This is a very simple program. All that it asks for, if we go to the very top here, it's called melody. It plays a melody. All it needs is a speaker on digital pin 8. So what I have here is one of the buzzers that comes with the kit, and then simply 2 of these little extension wires, 1 for each pin. I just happen to have red and white here. This other one kind of should be black since it's going to go into ground. One goes into ground, one goes into digital pin 8, and that's all that this one takes. You don't want to plug this one into power, this kind of buzzer, because it'll make a really high-pitched squeal. So you don't want that. But now we can hit upload. So you hear a pretty loud rendition of Shave and a Haircut. So how does this work? So just to break down a couple of things here. First of all, 8-ohm speaker on digital pin 8. There's no variable for the speaker in this particular program, unlike some of the ones that I tend to write, or the way that I tend to write my programs. In this case, we're just using the tone command, and the first variable for that is the pin to which this data should be written. So this is telling it, produce a tone on whatever it is that's plugged into tone to pin 8. And the information for that tone is this is the pitch, melody equals this note, note duration equals how long in milliseconds this should be carried out. So if we look above that, we see how these notes and durations are combined. So what we have here is a sequence of notes, and these actually work sort of in terms of real note names, you know, C4, G3. If you think about the way the keyboard goes, the notes are numbered in an ascending way, so that, you know, C1 is the first octave, C2, C3, C4 goes on from there. C4 is higher than G3, for example, and if we go through the notes, you get this sort of dun, 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 little rest, dun, dun, simple melody, dun, 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 dun. So those are the pitches. In order for this to have duration, what it's defining here, actually, it tells you in the comment, note durations 4 for a quarter note, 8 for eighth note. So this works very well because it's very intuitive, but it also kind of shows us the way that musical durations are actually determined as fractions. So one of the reasons to do this unit on the Arduino and to study how it produces music and sound is because it gets us thinking about the basic materials of music and the basic ways in which we conceptualize those things through our familiar Western musical notation in both pitch and rhythm. So in this case, for example, when it says 4 is a quarter note, 8 is an eighth note, what we actually want to do also is go down a little bit and see that what we have is another variable being set, which is 1,000. So remember, the Arduino works in 1,000 millisecond increments. And 1,000 milliseconds equals 1 second. So this program is working in absolute time. It's working in actual clock time. It's not using a musical tempo. A lot of times in a piece of music, you know, you say the tempo is 120, that's how many beats per minute, or the tempo is 100 or 140 or 80 or something like that. In this case, the tempo for an entire measure, we'll actually say, is 1 second. So there are 60 seconds per minute, which means there are 60 measures in this case, which means the conventional way of saying that the number of quarter notes per minute would actually be there are 240 quarter notes per minute. If you think of 60 seconds, the way that a quarter note works is that you actually take the duration of an entire measure and you divide it by 4, which is exactly what the code is showing us here. Quarter note equals 1,000 divided by 4, eighth note equals 1,000 divided by 8, etc. So if you take your 60 seconds, you're actually going to divide the length of the measure by 4, which means we multiply 60 by 4. That gives us 240 quarter notes per minute. And the Arduino actually sees this in something like that. It doesn't see a grid of measures that have different note values. It sees only absolute values. This thing lasts 1,000 milliseconds. This one lasts 250 milliseconds. So for example, each quarter note is going to equal 250 milliseconds because 1,000 milliseconds divided by 4 is 250. Then an eighth note, which is half of that, 1,000 milliseconds divided by 8 is going to be 125 milliseconds. So basically, you're giving it these values that it needs to divide by: 4, 8, 8, 4, 4, 4, 4, 4. And then each time it sets this melody, it uses a loop. Each time it sets this melody, it's going to divide 1,000 either by 4 or by 8, essentially. This is the loop that's making that happen here. We start with 0. Each time this goes, we add 1, so that this note, for example, is the first one, this note is the second one, this note is the third one. So that's what forces the program to move through. First it plays this C4, next it plays G3, next it plays another G3, and then down here in the other variable little array here is the first note is going to have the duration 1,000 divided by 4, then 1,000 divided by 8, divided by 8, divided by 4, and so on. So the whole thing works on essentially a little version of a loop that is just going to increment the value by 1. And for as long as this note is less than 8, it's telling you when you get to the 8th note, stop, which is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 notes in this melody. We stop at the end of that. So that tells us how the durations are working. That tells us how the loop is actually helping us select this is the first melody, this is the second note of the melody, and so forth. The final thing to think about is frequency and how that ends up being translated into note names that we can understand. So C4, G3, etc. What the Arduino actually does, it's very convenient, is it comes with what's called a library. It comes with this thing that's called pitches.h. And pitches.h is a library that can be included with any Arduino program. It appears in this other tab over here. You just want to put it in the same directory as your Arduino code. And pitches.h is just this table that defines the actual frequency of all of these different notes. So B0, a very, very low note, is going to be 31 hertz. That is 31 vibrations per second. It's extremely low, extremely slow in acoustic terms. Then we scroll all the way up through here. So if we think about where were we? C4, that's 262 vibrations per second. G3, 196. And then so forth. A3, 220. The program is put together to take advantage of these note names that we already know. Now, if you were interested in different tuning systems, one of the things you could do is go into pitches.h or create your own pitches.h and put in different values. This system is going to use something that we call equal temperament, which basically means that logarithmically all of the distances between adjacent notes are the same. But throughout history, there were a lot of different ways of tuning instruments that had sort of certain benefits and then certain drawbacks. So if you want to try one of those different systems out, you can actually determine what the frequency values should be, and you can create your own, say, justly tuned .h or quarter comma mean tone .h if you're into something like that. But anyway, this is just a library that the Arduino draws on and lets it work with actual note names. So this makes it a lot easier to write a melody in the Arduino. So if you want to write a melody with the Arduino, what you'll actually need to do is just start from code that's very much like this. You really could start with the interval melody here, the note durations, this little loop, and this little rhythmic line of code that creates the rhythms. Finally, all you have here is just a little bit of a pause. We want just a little bit of the no tone command, which turns off the tone. We want to wait just a little bit. That's the delay command. So we're going to delay here. We're going to stop the tone playing. And this is just to create, a little bit of space between the notes. A human player who is performing this would create a little bit of space here, and this forces the Arduino to do exactly that. If we didn't have that, it would just kind of rush through da-da-da-da-da-da-da, without leaving the kind of pause that you might expect to separate the notes from one another. So let me just play this through one more time. So we can see, just as a little demonstration, I'd like to mess with a couple of the notes here. Let's see. We're just going to throw a few slightly off notes. This should just kind of sound out of tune and a little bit strange, So I've just made this one F instead of G. I've made this one an E instead of G. It's just going to sound a little bit off. Pretty subtle there. I should make this a little bit more obvious. Let's do that. Let's mess this one up a little bit more. Yeah, so it doesn't help that this isn't the greatest speaker. This is just the cheap one that comes with the Arduino. You can even see it's getting a little bit out of its register. It can barely create that low C3 note. It really doesn't have that much of a range. But if you want to change note values, what you have to do is go through and change the pitch here, and you can also change the duration. For example, maybe I'll bring the original melody back, but I'm going to get rid of the short notes. So that now when we hear this melody, all the notes are going to be the same. We're not going to have the shade and dun dun, that effect where two of the notes are twice as fast. We're going to get dun 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 dun. So here's that. Yeah, so that worked just fine. Another thing you can do is you can go even larger proportions. You can use half notes here. For example, if I turn everything except for those two notes, that second and third note that are already supposed to be faster, if I turn these all into half notes, we can get the same melody with the same proportions. It's just going to be half the speed. So that's just a quick little demo of a couple of things, and let's move on to our next segment.